As I said already, when we calculate definite integrals, our final answer is going to be some real number. That real number can end up being a positive value or a negative value. So we're going to talk a little bit about how that occurs and what it means to have either a positive or negative value as our result. So we're not quite at the point where we want to actually calculate definite integrals yet, but we are going to look at what exactly it is that we're calculating when we calculate exact intervals, or I'm sorry, calculate exact areas. So if the area that we're trying to calculate, which is again is that area bounded between our curve and the x-axis, if that area that we're trying to calculate is above the x-axis, then that area is positive. If the area we are calculating is below the x-axis, then that area is going to be negative. And this idea comes from, if we're still thinking about rectangular regions, if we draw a rectangle above the x-axis, that has some width along the x-axis, and then its height is going up to, let's call this, say, positive 3. So we take this width, which if that's about 1 times 3 would be the area for that rectangular region, so this rectangle would have an area of 3. If we had another rectangle that also had a width of 1, but dipped down below the x-axis instead, that function value down there would be negative 3. So while the area of this rectangle would be positive 3 times positive 1, which would give us an area of 3, the area for this rectangle would be negative 3 times positive 1, or an area of negative 3. So if we get a negative value as a result, it means that our area, or the majority of our area, was something below the x-axis. So let's take a look at this with regards to the function below, in this case the graph of negative x squared plus 2. We could look at breaking this up into regions where we have positive areas and negative areas. So for instance, we have a positive area as long as we're considering values of x from negative 1.5 to 1.5. So the region between the curve and the x-axis here would be positive. And then if we consider from negative 2 to negative 1.5, here we have a negative area, since that space between our curve and the x-axis is below the x-axis. And again, we have the same thing occurring from positive 1.5 to positive 1.2. So when we calculate definite integrals, the process is going to look similar. We're still going to have that integration symbol. So we're going to integrate some function f of x dx. So that looks exactly like our indefinite integral problem. But now what we're going to include are some upper and lower bounds for that integral. So if we want to look at integrating this just where this is positive, that's from negative 1.5 to 1.5. So we could integrate this function from x equals negative 1.5 to positive 1.5. So without coming up with what exactly that area is, we know that that result is going to be something positive because the area over that interval is completely above the x-axis. Versus if we looked at finding the definite integral of our function from, say, negative 2 to negative 1.5, that area would end up being something less than 0. So the result of that definite integral, whatever number we come up with, would have to be negative since this area is below the curve. And if we looked at the integral from 1.5 to 2, that value is also going to end up being less than 0 because that area is contained completely below the x-axis. So let's look at actually generating some specific results here, some exact results. So what I can tell you is that the area under this curve from negative 1.5 to 0, that area is 1.875. The area from 0 to 1.5 is also 1.875. This shaded red region from -2 to -1.5, that area is approximately -0.5. And the same thing on the other end. So now knowing what the areas are for those specific regions, now we can look at actually calculating the exact area between the curve and the x-axis for some specific given values. So if in part A here, we want to integrate our function f of x over the interval from -2 to 0, that means what we're looking at is from -2 to 0, what is the area between our curve and the x-axis. So in this case, we have a positive region, 1.875, and then we're going to subtract or add that -1.5, so we're subtracting 0.5, which gives us a total area of 1.375. So at this point, we're still not really doing the calculus to come up with these definite integrals. We're still going to have to establish the process for this. But in this case, given the areas under the curve for these two regions, calculating that definite integral, if we know those areas, just comes to adding this region to this region and coming up with that final result. Similarly, in part B, if we want to integrate from 0 to 2, now we're just looking at values of x from x equals 0 to x equals 2. And now we just need to add any areas that occur over that range. In this case, we have the exact same values occurring. So we have 1.875 minus the 0.5 is going to be equal to, again, 1.375. So calculating these definite integrals comes down to finding the area between our curve and the x-axis, identifying whether that's positive or negative, and then just adding those different areas together. So in general, we won't know what these different areas are. It's going to be our job to apply calculus, actually use some theorems and techniques to come up with these different values.